Yo, 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 yo. Bam, 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 bam. All right. So today we're doing problem 847. It's been a while since I've done a problem older than 1,000, right? Probably coming before 1,000. Shortest path visiting all nodes. This is a pretty popular problem, right? I mean, it's old, so it's had a long time to get exposure. There's been 106K submissions, so probably there's a lot of other people that have posted solutions to this problem, but I just figured I'd do it today because I got to get through all the graph problems. So this is one of the last remaining problems that I need to do in order to finish all the Leetcode graph problems. Okay, that reminds me, please please subscribe. If you like the way that I do this, let me know in the comments below. If there's a problem you want to see me do, if you're like, man, I really like the way that you did this problem, and I want to see you solve this problem because I don't completely understand it, then just share the problem that you want me to solve below, and I'll go ahead and do it. Okay, so shortest path visiting all nodes. Okay, well, we think about shortest path problems, right? We can do Dijkstra's, we can do breadth first search, we can do depth first search, right? A searching problem. Okay, so you have an undirected connected graph. I keep doing that. An undirected connected graph of n nodes labeled from 0 to n minus 1. You're given an array graph where graph I is a list of all the nodes connected with I node by an edge. Okay, so it's not given as like this list of edges. It's actually given in a form that we usually deal with when we're doing graph problems, so that's good. Return the length of the shortest path that visits every node. You may start and stop at any node. You may revisit nodes multiple times and may reuse edges, right? So this is what makes this problem so difficult. This idea that you can start and stop at any node, okay, so there may be a more optimal path depending on which node you start at. So if that was the only constraint, I'd think, okay, I need to run BFS from every node. But also you may revisit nodes multiple times and you may revisit edges, right? So that kind of breaks one of the constraints of BFS, which is, when you run BFS and you go from one node to another node, you'll never visit the same node twice, right? Like you'll have this set, however you want to do it, but you'll have some sort of ledger that keeps track of what you visited. And if you try to visit something that you've already visited, it won't allow you to do that, right? And that keeps your runtime linear, because what you don't want to do is continue to check the things that you've already checked, and you're wasting operations, and it can get exponential very quickly. So this is like BFS, but you're removing one of the constraints that makes BFS optimal, that makes it time efficient. So this problem of trying to find the shortest path that visits everything sounds like BFS, but we need to somehow adjust the way that we run BFS, because we no longer have this idea of once you visit a node, you never visit it again, right? Because this is explicitly saying you can visit a node as many times as your heart desires. We're just trying to find the minimum path that can get you to every node in the system. Okay, so with that said, let's go ahead and look at this example problem. So in this example problem, we have node 1, which connects to node 0, which connects to node 2, which connects to node 3. And it's saying the optimal path is from 1 to 0 to 2 to 0 to 3. So from 1 to 0, from 0 to 2, from 2 back to 0, and from 0 to 3. Right, so you'll notice that in this example, you visit this node twice, and you use this edge twice. Right, so this is very dissimilar from other examples of BFS that we've used before. Versus in this system, you can actually run a standard version of BFS, right? Not BFS, but a standard graph traversal where you start from one node, you go to another node, right? Every node is unique in the path, every edge is unique in the path. You don't have to reuse edges or reuse nodes. Okay, well, since I said we're going to use BFS, right? that's kind of just something intuitively you'd have to recognize when you look at this problem, right? How would we adjust BFS to make it work for this system? Well, in BFS, right? In BFS, what do? Well, let's write, how are we gonna do this? Let's write a standard version of BFS that we use all the time, right? In a lot of problems, which is clean and concise. And then we can kind of build on these extra parameters, these extra features into that BFS to fit the kind of looser constraints of this problem, right? So how does BFS work? Well, BFS works by, you do, so let's just do a standard BFS. So if you had a BFS with a Q, let's say that the node you start out with U and it equals 0, right? You say, okay, U equals, you start off with this Q where U's inside of it, and then you have a scene array or scene set, which just tells you if you've seen something before, right? And if you've seen it before, you don't traverse it again. And then how does BFS work? Well, while there's something in the queue, you're going to update the queue to the next level by doing what? Well, you'll look at each node V. You'll add each node V to the queue for U in the queue for V in the graph at U. Right, and if I'm going too quickly here, if what? You'll only add the child if you haven't seen the child before. Okay, and then what you'll want to do simultaneously is, if you haven't seen it, this is just a quick way to one line add that child to the queue. Right, so basically saying I'm going to traverse this graph and I'm going to add the child at the next level if I haven't seen the child before and it's a child of one of the members currently in the queue. So if we just wanted to look at how this worked, starting from 0, we should expect the queue to be 0 first and then 1, 2, 3. V for Q and U if not U and not in scene, if V is not in scene, sorry. If the child's not in scene. If I haven't seen the child yet, then I add it to the queue. Right, so 0, 1, 2, 3. If we ran this from 1, we'd see 1, and then the next level would be 0, and then the next level would be 2, 3. So 1, and then the next level is 0, and the next level is 2, 3, right? Because built into this system in BFS, right, an invariant is that everything in the queue is at the same level, right? And level means the distance from the node that you started, right? So everything at 1 is distance 0 away. So maybe let's add that idea also into the system so you can see that. And then at the end of the thing, we'll just update the level. What am I doing? What's going on? Oh no! Don't look! What the hell? Stop. Dude. I love Apple products, but sometimes. Okay, so level we're going to update after each run to level +1. And then here, just to kind of debug, we'll say, well, the level is level and the queue is queue. Just so you can kind of see what I mean, right? So if you start at 1, then at level 0, we just have 1, right? At level 1, we have 0, and at level 2, we have 2, 3, right? Because you traverse this node and this node and this node. Now, this is kind of an idea, but it doesn't encapsulate this notion of, well, this path that we've just created, right? This path isn't a connected path, right? Because it branches off. The path that we're referencing right now isn't accurate because it's basically this, right? You go here, and then it branches off to this system and branches off in this system. So what if what? Well, I guess in this problem, this idea of scene is a state. It has states, right? And what I mean by states are places where you've been, right? Because when you go to 1, you've seen the state, which is 1. So you never want to visit that state again because it won't give you any additional information in BFS, right? You build a state 0. Every time you see a state, you add it to your queue so you don't visit that state again. And in BFS, every time you visit a node, you've cleared that state because any subsequent time you visit that node will have a longer path, so it's suboptimal, right? Every time you visit a node using BFS, that's the fastest way to get to that node. So there's no reason to visit that node again. So that's a state. The state is that node, right? So every time you see this state, you just disregard it, right? If I see the state 0 again after I've already visited 0, then this path is longer, so I've already visited the state of 0, so this path is suboptimal. Okay? So what would be a state in this system? Well, a state is kind of like, well, in traditional BFS, a state is the node you are traversing, meaning that a state is literally the node itself. So if I visit a state twice, I don't need to traverse it the second time because I've already done it. And I've talked about that now at this point ad nauseum. But in this problem, a state is really the path that you've taken, right? You could argue that, if you look at this problem, right, there's a difference between going from 1 to 0 and a difference between going from 1 to 2 to 0, right? These are different states. It's a different path that I took to get to 0. So a state is really what are the vertices that you visited before you got here, right? A state is no longer just the node itself. A state is what have you visited in order to get to this node, right? Because it's kind of the same idea, right? If you've gotten to this node and you've visited more nodes already, like this state, it could be a better path, right? Going from here and up, that could be a better path. But if you visit a state, I'm trying to think of a way to draw this. If you visit this path, okay, let's call this 4. You go 1, 4, 2, 0. But then some other person goes 1, 0, 2, 4, 0. Well, what nodes have been visited in both of these paths? So in the blue path, you visited, in what order did you do it? You did 1, 2, 4, 0. And then what about in the red path? And you did 1, 4, 2, 0. Now the order in which you've gotten to 0 is different, but you visited the same nodes, right? So if I've already visited these nodes to get to this node here, right? If you visited the same nodes to get here, then I don't need you anymore, right? Because since it happens in levels, if this happens somehow, let's just imagine it wouldn't match this problem. But say this happened at level equals 4 and this happened at level equal 5. If you've already gotten there with level equals 4, then if you get there with some higher level, right, then you disregard the path. You say, well, look, I've already gotten here and visited all the nodes that you visited, and I've done it faster. That's basically the idea, right? Because in a traditional BFS, if you visit a node again, and if you visit a state again, you can say, look, I've already visited this state, and since this process happens in orders of levels, if I've already visited this state, then I've already visited this state with lower cost. In this thing, it's the same idea. If you visit a state again, where a state is the number of nodes, a state is the nodes you visited, I've already visited this state, and I've already visited all the same nodes you visited, but since I've already done it, that must mean I've done it with a lower cost. So I'll disregard what you do. So instead of saying scene add node, what we need to encapsulate into this problem is, well, let's add all the nodes that we visited previously. And if we've already visited all those nodes previously, we don't want to we've already visited all these nodes previously. We don't want to add that to our queue, right? Because we've already done it with a lower level. And this basically encapsulates this idea of a path, right? Because a path is the nodes that you visited. Now, it doesn't necessarily matter how you visited those nodes in the path, but as long as you visited those nodes in the path, that'll create a state. So that also encapsulates this idea of actually traversing a path versus BFS, which says the things that you can reach in a certain level. Okay? So one thing I should probably add, right, is that we have to look at each node, correct? Because we don't know if the optimal path is going to start from here or start from here or start from here or start from here. So we're definitely going to have to look at each node. So we'll do for U in range the length of the graph. Okay. So then all this is going to get tabbed. And then we'll have a shortest path here. And we'll assume that it doesn't exist. So it'll be float infinity. And then how are we going to efficiently note, or like in a ledger, notice all the paths that we've seen before? And this is the idea of bit masking. So bit masking just allows you to, since these things are ordered, right? It's like 0, 1, 2, and 3. We can efficiently look at paths that were traversed already to determine if we've already seen nodes in a path. So the way that that's going to work in this problem, just to show you quickly, I didn't really want to go off on this tangent, but I think it's probably important for this path. So how would we capture 1, 2, 4, and 0, 1, 4, 2, and 0 efficiently in this path? Well, what we'll do is, let's say for this problem we have 0, 1, 2, 3, and 4. Well, let's write it back to its original system. So we didn't have this, right? So what we'll do is we'll create this bit string, not really, it's just a number, but let's represent the number as a bit string, which has length 4. And we'll call this visited, okay? And every time you visit a node, you'll set that bit to 1, right? So if I start here at 1, I'll then set this bit to 1. And then once I visit here at 0, I'll set this bit to 1. And then when I visit this node 2, I'll set this bit to 1. Now notice that, sorry, I probably should have done that. So every time we traverse, right, this was 1, and then it became 1, 0, actually, and this became 1, 1. So then our scene array would be 1, 0, and 1, 1, and 1, 1, 1, right? I'm just adding this goes here, this goes here, this goes here. And then once this thing comes back, it's going to ask, well, is... sorry, and then once you finish this system, all of these will get set to 1. So that means if all the bits are 1, then you've successfully traversed this whole graph. So I'm trying to think about is 1, 0, 2, 0. How would that not? Because wouldn't it say, okay, you've already seen. Ah, okay. So you can't just... damn it. Sorry, I just thought about this. You have to look at, in scene, you have to look at the nodes that you visited and where you're at. Right? Because like the difference is when you get to 2, you visited 1 and 0 and 2, right? But you can get somewhere else and visit the same set of nodes, and it might be more optimal. So in order for a state to be visited already, in order to have a state that's suboptimal, that means you've visited all the same nodes and you're at the same node. You're basically at a cycle, right? You visited all the same nodes and you're at the same node. That's why you can visit 0 again here, because you visited all the same nodes as 2, but you're at a different node. If you were to reach 0 again, where you visited all the same nodes and you're at 0, then that's a state where you've already visited something, okay? So we'll use this visited string to represent what you visited, right? And just to kind of go over it quickly, if I had a visited string that looked like the following, right? If I said visited was that would mean that 3 has been visited, right? Because of this is 1. 2 has not. 1 has been visited. 0 has been visited. So that would mean that this has been visited if I just looked at this visited string, right? And I can quickly compare 2 visited arrays by just comparing 2 integers, right? Because this is actually an integer. So if I had visited and visited prime, I would know that they're equal just by comparing them as integers. If any of the bits were different, then they wouldn't be equal, okay? So that's basically the problem. So we're going to look at each U. So we're going to start at each U. The Q is then now not just U. We should look at U, because U used to encapsulate the state. So all we had to have in our Q was U. But now the state is the vertice itself. We don't need to do it like that. The state is the vertice itself and all the nodes that you visited to get to this vertice. So when you start out, the only vertice you visited is yourself. So in order to make that into a string, you're going to take 1 and you're going to bin shift it U times. Right? When you start this problem, if I start at 1, so I have this bit, if I start at 1, I can take a 1 and shift it over to the left once, and then I have this. So that basically allows you to bit shift a 1 into the correct position to notate that you visited that vertice. And then you create a set the same way. And then, well, how do we know that we've visited all the nodes? Well, that would mean that we say there's this all visited string, right? The all visited string is all ones. So for this system, an all visited string is 1, 1, 1, 1, right? So how would you quickly use bit masking to get 1, 1, 1, 1? Well, you can look at how many nodes are there. There's 4. So if you bit shift 1 4 times, you get 1, 0, 1, 0, 0, 1, 0, 0, 0. This is the first shift, second shift, third shift, and then 1, 0, 0, 0, 0. So fourth shift. And then if you subtract 1 from that, so you subtract 1 from this line, you get 1, 1, 1, 1. Right? So if you take the length of the graph, shift 1 that many times, and then subtract 1. So you take 1, you shift it the length of the graph, and then you subtract 1 from that, you'll get the appropriate length of the appropriate state of all visited where they're all ones. Okay, so what we then do is we look at a state and we say, well, if we have a node in the queue where all of the nodes have been checked, that would mean that its value for its visited would all be 1. So that would mean it was equal to all visited. So if any of the node visited equals all visited for, well, there's the node, and then it's, because we don't care what node you end at or what node you start at, we just want to find the length, the minimum length. For node visited in queue, we'd say, okay, maybe this is an optimal path. So we'd say, okay, hopefully this is the shortest path. So we'd say the shortest path is the min of any previous shortest path we've seen and the level that we're currently at, right? Because every single time we traverse this thing, we find another level and then we break because we're done. We don't need to look at the rest of the things in the queue because the queue is always has the lowest remaining nodes in terms of level, right? Any traversal after this will have a level equal or greater. So this is the best it's going to get in this case. Okay, so then how do we add things to the system? Well, the system still has the vertex v, but we have to add this node visited state. And we have to OR it to add in the additional node to the additional node. We don't want to just add in that because we could have a node we've already visited once, but in a different way. So if we OR it, we'll just set that bit to 1, meaning that we visited that node. And it's the same idea here, right? You take 1 and you shift it over to the left v times. For u and node visited in queue, for v in graph, if we've already visited this node and its counterpart, not in scene. Otherwise, we're going to add this node not in scene into the system. And then that should be it. So then at the end, we'll just return the shortest path. Set add takes 1 argument, 2 are given. Okay, so I forgot to capture this in... Yeah, let's submit it. There you go. We got a solution. Now let's try to get cute and make it really short. So what's the runtime of this? Well, this is really slow because a state is no longer just a node. A state is a node and all the previous nodes that you've traversed. So that's going to be 2 to the n time, right? That's an exponential system because each bit can be 0 or 1. You have n bits, so that's 2 to the n bits. And then you have to look at each node in the range. So you have to do that n times. And that whole process traditionally takes n times. So this is n for this outer loop, n for this inner loop. And then n for this inner loop traditionally, and then 2 to the n times n because every single node visited path, right, there's 2 to the n states that you could possibly traverse. So that's there's n times 2 to the n possible states that you could traverse, right? Because there's all the states you've traversed, which is 2 to the n. I mean, all the possible combinations of nodes that you visited, which is 2 to the n, and all the possible nodes you could be at, given all the possible nodes that you've previously traversed. So that's 2 to the n times n, and this takes n, so that's time n squared times 2 to the n. So it's pretty slow. Okay, but it's fast enough to pass. So, and don't worry about this runtime. This is the same as the best, just that I did a little trickery to make it a little shorter, and that always screws up your path a little bit. So what's the space? Well, we have to remember every state. It's only for a level. Well, there's 2 to the n states that we might end up having to go to. But every single time we go through a node, we disregard what we've seen before. So we cut off a one of the ends, right? Because for each of these ends, we build a new system. So every time we look at it at another node, we disregard what we saw before. So we're not going to hold on to n squared information, only n information. Okay. And with that, I bid you adieu. This is a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 aligned solution. Peace out.